the kind of acids that we're going over, there are several different definitions of acids and bases. One is like electron acceptor, electron donor. Then there's proton acceptor, proton donor. Then there's one that produces H plus and one that produces OH minus. So for us, we're going with the Bronsted-Lowry definition, and those have to do with being proton donors and proton acceptors. So when I say proton, they use this word to mean H plus. Yeah, if we get a chance, we will go over the quiz. You'll probably know the answers as we go over the lecture too. So proton donor just means something that gives off an H plus. Proton acceptor is something that will take one. So if I had sodium hydroxide and I put it in water, the sodium would break apart and the hydroxide would break apart, and the OH minus would have negative charge, so it's perfectly situated to take an H plus. So if it takes the H plus, then it must have been a base. If it donated the H plus, it must have been an acid. Well, let's see if there was anything else. Oh, also, I don't know if we went over hydronium in this class or not, but hydronium is given in this equation here. So if you have H plus, which is donated by the acid, then you get H plus floating around in water. It tends to grab onto the water and become part of the water. It'll join the water and produce an H3O plus. So a lot of times people will use the term H plus, proton, and H3O plus and hydronium. They all mean the same thing. I don't think H4O plus does, because then it would be actually H4O2 plus, and I think it'd just be too much for a water. It'd be too positive for that. There's probably a way in a lab somewhere that you could force it to happen, but it wouldn't normally happen. But that's a good question. All right, see if we missed anything else. Okay. Yeah, they went over like this. This is the shortest net ionic equations section I have ever seen. So if you look, where does it start? I guess technically it starts right here at the top with equation 813, right there. Starts talking about net ionic equations and acid-base reactions. Acid-base reactions are neutralization reactions. So where an acid comes in and there's a base, so like HCl and sodium hydroxide, which is in this reaction here. The H and the Na switch places. So if you look on the left, the H is with the Cl. If you look on the right, the H is with the OH. It's kind of harder to see because they wrote H2O, but that's the same as HOH. So that's water there. And then the sodium on the left is with the hydroxide part, the OH. And then the sodium is with the Cl on the right. So the H and the Na switch places. And so then you have water that was produced. And because it's not happening in a combustion reaction, it's just a liquid now because it's happening at room temperature in solution. So it's just going to produce a little bit of water, not enough water to really matter, just a little bit of water and a little bit of salt. So, and when I say salt, I just mean ionic compound. So a neutralization reaction, when you get an acid and a base and you produce salt and a water. And a strong acid will just have the one arrow to the right, and a weak acid like acetic acid will have those half arrows to the right and to the left. So it'll have like double arrows pointing in each direction. Just saying it goes forward, it falls apart, it goes backward. All right, and then they have the different types of equations. There's molecular equation, the overall ionic equation, and then the net ionic equation. No. NaCl is a salt. So you have, actually, hang on one second. Let's see if I can find where I put all my stuff this morning. Oh, not good. I'm about to drop all my things. Okay. Give me 1 second. Let me pull up a whiteboard here. And let's see. Where was that? Okay. Yeah, sodium hydroxide is the base. All right, so I'm going to switch this over to my tablet. It'll take just a second. All right, let's move you. Wrong direction. Let's go the other way. Okay. Come on. I'm encouraging my computer. You're wondering, what am I talking to? Sadly, I'm talking to the tablet, which is kind of a pointless thing to do. Okay, so we have HCl plus NaOH makes, and then the H and the Na are going to switch places. So that'll be NaCl plus HOH, which is the same thing as H2O. Yes, in an acid-base reaction, they do always switch places. And here is an ionic compound that we call a salt. Now, in this case, it's also what we normally call salt, like table salt, but it doesn't always end up in table salt. Sometimes it could be like potassium bromide. We would call that a salt also, but we wouldn't eat that, right? And then this is just water. It's going to be a liquid. It's going to be aqueous, aqueous, and aqueous. Now, looking at these things to see which one has a hydrogen to donate, this one doesn't, because if we look at what it breaks up into, it has an Na plus and an OH minus. So if it donated the hydrogen, then it would just be O2 minus, and then that is going too far, right? It's not actually going to do that. It's not going to break up into its elements. Now, the HCl, because this is held together by a covalent bond, but the OH minus and the Na plus are held together by an ionic bond. Now here, this is going to fall apart into H plus and Cl minus. So here we have an H, and here we have something that's negative, so it could combine with an H. So that means this has something that can take a hydrogen, so that makes it a base. And this has a hydrogen to give away, so this is an acid. And the H plus, they also call a proton. They also, because if you have hydrogen, it's just one proton and one electron, so you take off the electron, you're left with the proton. So it's called a proton, H plus, H3O plus, and hydronium. Hydronium is H3 plus. And H plus and the proton, same thing. But a lot of times all four of these are used interchangeably. So the base is going to be the thing that will take the hydrogen. Most of your bases will have hydroxide, so an OH minus. And the other one that we'll study is ammonia, which is NH3. NH3 can easily become NH4 plus. Notice it going from 3 H's to 4 H's. So this is a base because it will frequently take the hydrogen. Now let's take a look at it from the ionic equation perspective. So we've got sodium chloride, I'm writing the exact same thing. Hang on one second. Let's see. NH4 actually would be an acid. But I don't think we're going to get too much into NH4 being an acid. That goes more into kinetics, which is something they talk about in 1212. But technically it would be considered an acid. All right, so we said that the water is going to be a liquid. Sure, no problem. Let me finish this one first, and then I'll get to titration. All right, and then this was aqueous. Remember, aqueous just means dissolved in water. Right, so this is called the molecular equation. My stylus is skipping today. All right, so the next thing we want to learn about is the overall ionic equation. All right. So with the molecular equation, everything is together, like a molecule would be together. So that's where it gets that name, molecular equation. What did I put? Yes, it should. Okay. Yeah, this should be HCl, guys. I'm so glad you pointed that out. Okay. That would have thrown a lot of people off. Okay, so we have some things with aqueous symbols, and then we have the thing with the liquid symbol. Everything with the aqueous symbol that's an ionic compound will be actually in solution apart. Remember, they dissolve, so they fall apart. So we would have H plus plus Cl minus plus Na plus plus OH minus makes Na plus plus Cl minus plus, and this is important, if you see any of these symbols, if you see a liquid, a solid, or a gas, don't split those up. Those stay together. Correct. You will split up all the aqueous ionic compounds. So you will want to go back and review those polyatomic ions so you can recognize when it is ionic, and so you remember the charges. That's important. All right, so that means for the water, right here, it's got a liquid symbol, so we're not going to break that one apart. And this one is already balanced, but I'll give you an example. Let's see what time it is. We'll go a few minutes. I'll try to give you an example where it's not balanced. Well, no, that's not what I mean. Where it's balanced with coefficients in a couple of minutes. Okay, so we've got all of this. Now, some of the stuff on the left and on the right is the same. If it's the same, we can cancel it out. And that's because those ions aren't really doing anything in solution except floating around. Because if you look on the left, the chlorine is Cl minus Aq, and it's identical on the right. So nothing really happened to it, and nothing really happened to the sodium either. What's happening is the H plus is joining with the OH minus to make water. The reason that we say that we have NaCl on the right, actually what we just have is we have ions floating around in solution. If we remove the water, all we have left is Na and Cl, so they have to come together. But for the most part, if we're looking at it in solution, they're aqueous ions on the left and they're aqueous ions on the right, so we can ignore them because they're not the main thing that's happening. They're called spectators. So spectator ions are the ones you cross out. They're the same on the left and on the right. And you'll be asked to identify spectator ions a lot. All right, so then the net is the overall ionic equation. And then this is the net ionic equation. And technically, the overall ionic equation doesn't have everything crossed out. I crossed those out so you can see what's a spectator ion, and so you can see what to write in the net ionic equation piece. So we have H plus OH. Those are both aqueous. Makes water. So if you have worked at a job before where you get paid like Wendy's or something, they have what you call a gross paycheck and a net paycheck. The gross paycheck includes everything. Everything you earned, you'll see in the gross part. Now the net is what's left after the government takes their piece. So usually it's 75% of what you earn. So this is like the net paycheck in that there's less there. So you take out the pieces that are identical, the spectator ions, and what's left is the net ionic equation. Now, if you look at this equation right here, there's only one thing that doesn't get separated. That. So you know that's going to be your product. And there are only two things on the left that lead to that. That would be the H and the OH. So you can actually get to the net ionic equation without ever having to go through the overall ionic equation. But it's good to be able to know how to go from the beginning all the way through these problems. And the reason is because a lot of times it'll ask you what your spectator ions are. it might ask you what is the overall ionic equation. Now, even if we did it the shortcut way, where I say, okay, this is my product, this and this is where the product comes from, then everything that wasn't where the product came from would have to be a spectator ion. It's kind of a shortcut way, but while you're learning it, I would recommend doing it the longer way. Just keep the shortcut method in the back of your mind, so that as you go through it, you can, like if you get to the exam and you forget this kind of stuff, just remember that whatever's not aqueous is going to be your product. And so sometimes that'll help you narrow down the question answers. All right, let's take a look at a titration problem. We'll do some more complicated ionic compounds as we go through there. Now, remember to keep in mind that you need to be memorizing the strong acids and the weak acids as you go through that. There are 2 tables on the periodic, in the book in section 8.4 that go over that. And then you'll also be studying the strong and weak bases as well. Come on, computer, do something. Okay. So this is all the way to find products from the balanced equation. Yes, that's the way to find the product from balance. That is correct. Now we're going to take a look at titrations. All right, so you've probably done a titration in the lab where you have a burette. Looks like this. And then you have a flask. It's like this. And then you'll have some liquid in the burette, and you'll have some liquid in the flask. In one of these flasks, either the flask or the burette, you'll know the molarity. And that would be the titrant. Right? So that's the titrant. That was one of the quiz questions. And then the other one, the one that you don't know the concentration of, that's the analyte, because we're analyzing it. And the whole purpose of a titration is to find the concentration. So we're going to find the molarity or concentration in whatever units we decided we wanted to work with. And then we have the equivalence point and the end point. The equivalence point is where there's an equal amount of acid and base. Let's see. Well, that's strange. Come on. Oh, I won't do what I want. Okay. All right. So let's do an example. Oh, and then there's the endpoint, and the endpoint is where you have an indicator that changes color. And it usually changes color in a specific pH range. It doesn't necessarily change color. It's not necessarily exactly the same as the equivalence point. The reason is, hang on, let me find my mouse again. All right, so we've got equivalence point. They may not be exactly the same thing. We use them to calculate it almost as if it was exactly the same thing, kind of. The equivalence point, it depends on which method you're using, whether you're using a pH monitor or whether you're using an indicator. If you're using a pH meter, the equivalence point will be at 7, and that's showing you that everything, well, not technically, because you do have to graph it. Anyway, they're pretty similar. So they're pretty similar. Quiz had a question that said that was what it was. Yes, it basically is the end of the titration. But it's more than the end of the titration. It's where you have equal moles of titrant and analyte. So let's do an example. You're welcome. All right, so we'll just do a simple example. All right. All right. So let's say we know that, and I did this again, this should be an H. We know that our HCl contains, so let's say we mix up an HCl solution, and we know that we have 10 milliliters of 3 molar HCl. And it requires 53 milliliters of unknown molarity sodium hydroxide. So, yeah, it's supposed to be HCl. Right here. That's HCl. All right. Let me make it more like your labs, and I'll make this. Oh, I think this would work. Yeah, that'll be fine. Okay. So the first thing we want to do is we want to find out how many moles of HCl we have. And a lot of times, like if you use KHP in the lab, that was a powder that you would measure out, or crystals you'd measure out. Then you mix it and swirl it, and in 10 milliliters, well, not necessarily 10 milliliters of water, but in some amount of water. The main thing is not how much water is in the flask. The main thing is how many moles are in the flask. So let's say we have 10 milliliters, so that would be 0.010 liters of hydrochloric acid. And we know that it's 3 molar. So in 1 liter, how many moles are there? If it's 3 molar? 3, right? All right, so now we're at moles of HCl. We need to get to moles of sodium hydroxide to be able to figure out what the molarity is. So we have to go from moles of one thing to moles of something else. What would we use? Coefficients, correct. So the coefficients for everything here are all ones, but if they weren't, we would just use those. Yes, yes. You would want to convert to liters. All right, so we have 1 mole HCl, and that's coming from the coefficients here. 1 mole NaOH here, and then that's going to be 0.030 or 30, well, 0.030 moles of NaOH. Exactly, yes. All right, so now that we know how many moles there are, what's the next step to figure out the molarity? Correct, moles per liter. Right, and we know that we have this many moles, and the problem told us that we have this volume of sodium hydroxide. Correct. All right, so our molarity is going to be equal to 0.030 moles of sodium hydroxide per 0.053 liters of sodium hydroxide. So you're going to put that in the calculator, and that will give you your molarity. All right. So there are a couple things to make note of here. One is that if you're going volume to moles, use molarity. If you're going moles to moles, use coefficients. And then keep in mind that molarity is moles over liters. So once you find out how many moles of sodium hydroxide there are, you're not quite finished. You've got to turn it into molarity. You could also go moles to volume as well if you had molarity. In this case, you could use M1V1 equals M2V2, and that's because everything is in a 1-to-1 ratio. When it's no longer in a 1-to-1 ratio, you can't use it anymore. Now, in this case, we have a monoprotic acid, meaning mono meaning one, protic meaning proton. So HCl has one H and one Cl. So that's gonna, in this case, since we have sodium hydroxide, everything's gonna be 1-to-1. Now, we can do another example.
Somebody's sleeping in class.
They've got a good example with sulfuric acid in the textbook.
Right now?
I'm pretty sure you guys have to do a sulfuric acid one in your lab. If you look on page 357, there's an example of how to do that, how to set that up. Let's do one with phosphoric acid. And we'll mix it with sodium hydroxide. All right. So to do this, Let's see what time it is. Oh, class is over, guys. Sorry. All right. Thank you, Chad. You are correct. And I will let you guys go. If you want to see some more of this, I'll be there during office hours today, so feel free to stop by. We'll continue this again tomorrow. Make sure you do your readings for the quiz on Wednesday. You're welcome. You guys have a good day.